So let's look at a few more graphs here, thinking about that idea of the inverse function. And then also what we'll get is a comparison here of exponential growth versus exponential decay and how those change with making our logarithm. So in this first graph here, we have our function 3 to the x and graphing the inverse function. So the inverse function here will be a logarithm, and then the base will be 3 of x. So what we can do is focus on a few points here. So that's 0, 1, 1, 3, and then if it helps that like -1, 1/3 would be there as well. So kind of tracking those 3 points, and there are even more, like at 2 we have 9. And what we're going to do is flip those coordinates. So like where I have 2, 9, now I'll have 9, 2. And where I have 1, 3, now I'll have 3, 1. 0, 1, 1, 0, and then -1, 1/3, now I'd be at 1/3, -1. So with that, we get our graph out. That would look something like this, where we'll be along the y-axis and then go off to infinity in that direction. So where the x-axis is kind of the barrier for our exponential function, the y-axis is our barrier for the logarithmic function. So let's talk about domain and range here. So 3 to the x versus log base 3 of x. So domain and range. So for exponential functions, domain's going to be all real numbers, and the range will start at 0 and go off to infinity. For a logarithm, that flips. So the domain is going to be from 0 to infinity, and the domain will be all real numbers. Did I flip that? Range is all real numbers. Sorry. All right. So what we just want to keep in mind is that domain, which again is telling us what values we can have for x. We're saying it starts at 0 but does not include 0 and goes up to infinity. So in terms of our logarithm function, that's telling us what we can plug into inside the function. We can have anything from 0 off to infinity, not including 0. So what we know is for our logarithm function, x has to be strictly larger than 0. Let's look at our exponential decay here. So this is coming from an original function that is exponential, but we have that 1/3 to the x. So we get that exponential decay when the number's between 0 and 1. So some key points we have here. We have 0, 1. We have -1, 3. And we have +1, 1/3. So what we can do is flip these. So where we have -1, 3, now we'll have 3, -1. Where we have 0, 1, we'll have 1, 0. And where we have 1, 1/3, now we'll be at x equals 1/3, y is 1. And we can even grab another point. We can see that -2, 9 there. So we can have 9, -2. That helps to have that extra point. So how this one's going to go is it's going to be coming from positive infinity and go along that y-axis, and then it'll increase off to, or decrease off to, -infinity. So it flips, just like how the exponential function flips direction across the y-axis. The logarithmic function flips across the x-axis in terms of behavior. So when you have exponential growth, see it come from -infinity and grow off increasing to positive infinity. When you have exponential decay, where our function's decreasing down to close to 0, with our logarithmic function, it's coming from positive infinity and decreasing off to -infinity. So, domain and range. So our original function is that 1/3 to the power of x. Our inverse function is a logarithm base 1/3 of x. So our domain and range. So for our exponential function, domain is all real numbers, and range starts at 0 and goes off to infinity. So exponential growth decay doesn't change those. It's always input is all real numbers. We can plug anything in. Range is 0 to infinity. Then for our logarithmic function, we just flip those. So domain will start at 0 and go off to infinity. Range is all real numbers. So with that, we can see exponential growth versus decay doesn't change the domain and range. That'll stay the same. So for this case too, the domain showing us what we can plug in for x, and the rule is going to be that in order to plug in a value for x, it has to be more than 0. So this is going to be a rule that we use in order to find what's the domain of our logarithmic function. And that's what we're going to do next here. We want to state the domain of these different functions, and we can do this without graphing them, although with one of these I will talk about the graph a little bit so that we can start thinking about our transformations. But the rule is going to go that if we're focusing on finding the domain of a logarithmic function, and we're taking some logarithm base b of whatever our input is there, it could be, it could just be x, but what we'll see is we could have some expressions in there as well. And it doesn't matter okay, I don't want to say that. It does matter the expression in there, because there could be limitations to the expression. But in general, it's just whatever is inside of there. What we just talked about with our domain is that whatever's inside the logarithm has to be more than 0. So in general, for solving these, what we're going to do is take whatever's inside the logarithm there and say that has to be more than 0, based on what we just talked about with our domain limitations. And then once we have that inequality, we'll just solve. So let's try that out. So where it's just f of x equals logarithm base 5 of x, I don't really need to worry about the base there. All I'm worried is about the input of the function. And what's being input into the function is just x. So what we would have is x, and then I would just take that and say more than 0. And there's nothing to solve there, so that's just our domain. Our domain is that we'll start at 0 and not include 0, and then go off to positive infinity. So just like we saw for our logarithm functions up above there, it doesn't really matter the base of the logarithm. If nothing else is going on inside the function and it's just your input x, then your domain is 0 to infinity. Whereas this next one, the input for our function is x minus 1, so it's this expression. So what we want to do is take that expression, x minus 1, and say that has to be more than 0. In order to input that into a logarithm, that has to be more than 0. And then we can solve and find that x should be more than, and we add 1 to both sides, so x has to be more than 1. So our domain would be starting at 1, but not including it. We want parentheses, and then going off to infinity. Now with this one, let's talk about the graph for a moment. So with our logarithm functions and our graphs, we talked about how there's this vertical asymptote at x equals 0. And in that last video, I talked about how that can move around with a horizontal shift. Well, in this right here, that minus 1 is giving us a horizontal shift. It's a horizontal shift right. So when we have subtraction, it moves to the right by 1. So without even getting too detailed in the graph, where my vertical asymptote would usually be right at the y-axis, we're picking that up and moving it to the right 1. So it's now our asymptote's there, so if I made a graph of our function, it would look something like that. It would be our logarithm function, and since it's a base 9, it would kind of be like 9 to the x, so we'd have an exponential growth. So it's a growing function, and it's just moved to the right by 1. So with this, we could see how our domain would start at this barrier of x equals 1, but not including it, and then we'd have all values off to positive infinity. Okay, with this next one, we have this expression inside our logarithmic function, and what we want to do is find where is 1 over x minus 3 more than 0. And something I'm also going to keep in mind here is that this function that's inside, we cannot plug in 3. So I'm just going to make a little note to the side that we cannot allow x to equal 3, because then that would give a denominator of 0. So this is like a composite function. We have this layer of two functions. We have this rational function on the inside and this logarithm on the outside. And we talked about this combination of domains when we have our composition functions. So we have to think about the domain of our inner function, which is going to be that we can't allow 3 to happen there. And now we're going to think about this domain as a whole, which is that whatever's inside the logarithm has to be more than 0. Now, our algebraic methods of solving here are going to be tough, because if I multiply both sides by x minus 3, well, multiplying by x minus 3 is just going to turn that all to 0, and then we lose our variable. So instead, what I'm going to do is think about the graph. So I'm going to be using the graph of 1 over x minus 3. And using that graph, I'm going to think about where's that graph more than 0. So I'm going to make just a little sketch over here because we just need some key values. It doesn't need to be perfect. So this function here, thinking about our graph transformations, our basic function would be 1 over x. So our rational function, which typically looks like this. Rough sketch there. But then what we did is we're subtracting 3 from x, so that means we're moving it to the right 3 units. So what I'm going to do is pick up this graph, and really what's going to help me is thinking about moving this vertical asymptote. So that asymptote's going to move over 3 units. So that's at 3. And then there aren't any other transformations, so my rational function would look like this. It's just moved over 3 units. So I want to know where this function that I just drew in blue, where is that more than 0? And that is happening right over here. The outputs are more than 0 on that side of the graph. So in terms of x values, we can't plug in 3, which actually matches up perfectly with our rule that we said there, but we can plug in any x values larger than 3. If we plug in values of x larger than 3, we're getting outputs more than 0. So what I'm seeing from this graph is that x has to be strictly more than 3. So our domain would start at 3, but not including 3, and go off to infinity. Now, with all of that work and using the graph, let's just make sure it works. So let's say I plug in x equals 5, just choosing something that lands in that domain. So if I plug in a 5 right here, I would have a 1 over positive 2. So I'd have a positive 1/2 in there, which works great. I can evaluate that. But if I chose something outside of this domain, like let's say I chose x equals 0, so if I plug in 0 right there, I would have negative 1/3, and we can't plug in negative numbers into a logarithm, so that would fail. So that's a bit of a tricky one, but the idea is that if we can't solve algebraically, look at the graph, and the idea of solving for that graph more than 0, well, you're thinking of where's y equals 0, and we want everything above y equals 0 since we want more than.